Okay, I guess I should start. So good morning, everybody. This is my last lecture. I'm going to wrap up our discussion of Majorana-based quantum computation. Let me just start by reminding you of where we were last time. We were exploring the question of how do you actually detect the presence of a Majorana zero mode in a topological superconductor once you've actually made one in the laboratory, following the kind of designer topological superconducting approaches that we summarized last time. So the most common method of trying to verify the presence of a Majorana zero mode is using transport, so trying to tunnel electrons onto that zero mode and finding some anomalous response. So I was viewing this as this Majorana tunneling problem as a scattering problem. So to set up the problem, we started thinking about a trivial gap superconductor that didn't have any Majorana physics whatsoever, and then hooking up a lead, which is held at some low bias voltage V, where low means small relative to the gap in that superconductor, which is grounded. Okay, so that lead can support electrons which propagate towards that trivial superconductor. The electrons can't by themselves hop into the superconductor because of the gap, so they can't directly tunnel. So there's no normal transmission in the language of scattering theory. But there's two different kinds of reflection processes that can arise. An incident electron can just bounce back to you as an electron. If that happens, you don't get any contribution to current flowing to ground. Alternatively, that electron can come back to you as a whole. That's so-called Andreev reflection process. Andreev reflection transmits a Cooper pair into the superconductor. There is no barrier for Cooper pairs to be absorbed in that superconductor, and that Char-2e object can then flow to ground and contribute to current. Okay, so the conductance of such a device, which is defined as the derivative of the current flowing with respect to the applied bias voltage, has this form: 2 times the conductance quantum times the probability of Andreev reflection. So if you want to make a prediction, you have to just infer the probability for Andreev reflection, and that you can in turn back out from solving for the wave functions in such a device and backing out the reflection coefficients. Okay, so we wanted to apply this logic to tunneling onto a topological superconductor. So here's the geometry that we're going to now continue to look at. I have a topological superconductor on the right-hand side with a Majorana zero mode sitting on the left end. I'm going to try to tunnel onto that Majorana zero mode and understand its response. The lead is on the left-hand side. I described the lead in maybe a somewhat funny way, which I'd like to elaborate on because maybe it was not so clear last time. So the Hamiltonian for this structure consists of two pieces. There's a piece describing kinetic energy for electrons in the lead, and then there's a tunneling term which hybridizes the lead with that Majorana with some coupling T. Okay, so for the lead, I tried to simplify this problem as much as possible, and so I described the lead just with a single fermion field psi of x, and I took a lead Hamiltonian, which just consists of this kind of kinetic energy for that field. Okay, so minus IV psi dagger dx psi, if you can diagonalize that Hamiltonian just by going to momentum space, and you find that the energy versus momentum is just linear like this, right, with a positive slope. And so this means that with respect to my x-axis coordinate system, these fermions are always right moving. Okay, but right moving should be viewed in quotes. The way I'm actually setting up my coordinate system, I'm bending the coordinate system so that x equals minus infinity is up here, x equals 0 is here, and x equals plus infinity is down here. Okay, so for x less than 0, those right-moving modes correspond to incoming electrons, and for x greater than 0, those, again, quote-unquote right-moving electrons correspond to outgoing modes. Okay, so we have both incoming and outgoing modes, which is, of course, what you need in a physical lead. Okay. So I hope that clarifies a bit that form. Okay, so for the other piece, HT, I wrote down T times gamma multiplied by psi of x equals 0 minus psi dagger of x equals 0. So microscopically, this kind of coupling between the lead and the zero mode just arises from microscopic tunneling, ordinary electron tunneling from here to here, projected into the low energy manifold. And by low energy manifold, I mean ignoring all the gapped excitations in this topological superconductor and just projecting onto the zero mode subspace. Okay, so I gave as a homework assignment to solve for the wave functions for any energy. I didn't give you a due date, so I won't ask if anyone solved it yet. But I'm not going to do that. As I said last time, I'm just going to examine two extreme limits where we can invoke some simplifications to make more efficient progress and not have to go through a very brute force tedious calculation. All right, so in particular, I want to look at the limits where the energy for the incoming electrons that you send in from the lead is much greater than t squared over v and much less than t squared over v. So last time we already solved the case where energy is much greater than t squared over v. Somebody wisely suggested that in that regime you can just do perturbation theory, and I just wanted to do the crudest possible thing, just do zeroth order perturbation theory, and just completely ignore the coupling to the Majorana to lowest order approximation. Okay, so in this case the problem becomes trivial to solve. My Hamiltonian just reduces to a Hamiltonian for the lead, and that's it. So we just have kinetic energy, and we know that the eigenstates are just ordinary plane wave eigenstates, which are created by operators dE dagger, which is just has the form integral in x e to the I e over v times x times psi dagger of x. Okay, so e over v again is just the momentum. So it's useful to plot the wave function amplitude for such scattering states as a function of x. So there's only an electron part here, and the wave function is just a complex phase, so there's no spatial structure, it's just a constant. And there's no whole part here, so the whole part of the wave function is just 0. So what this tells us is that any incident electron that you inject into the system, so incident electrons correspond to this part of the axis, those guys just get normally reflected as electrons. So there's no Andreev reflection in this limit. Effectively, the lead and the Majorana decouple at those large energies, and so the conductance, again, at energies, if you're probing the system at energies much greater than t squared over v, is approximately 0. Okay, so that's just a recap of last time. Any questions before I look at the more subtle case where we're looking at small energies rather than large energies? Everyone happy? Okay. All right, so let's now try to look at the opposite limit where E is much less than t squared over v. In this case, I need to consider ht more seriously. And to sharpen the problem, why don't we think about constructing zero energy wave functions, and we can take the limit where, let's say, that coupling t goes to infinity. Okay. So my claim is that there's some simplifying approximation we can make in this limit, which allows us to basically immediately write down the solutions for those zero energy wave functions, if we view the problem in the right way. So maybe let's ponder this for a second, and let me know if anyone has any ideas for what this term does when t goes to infinity. I'm looking at very low energy wave functions. So there's two ways in which you can phrase this simplification. One is in terms of some property of operators, and alternatively you can phrase it in terms of properties of wave functions. Any ideas?
Maybe you can represent fermions in the lead as Majorana fermions again, and then this Majorana will couple to the Majorana in the lead.
So that's actually an interesting suggestion. You can indeed do that, and what you would see actually is that so psi minus psi dagger would just pick up the imaginary part, and so half of that fermion would not couple to the Majorana, the other half would, but then we'd still have to figure out how to satisfy this coupling ht. So one could do that, and in fact, that's what I originally did to solve this. But I think it's simpler to not invoke a Majorana representation for psi. So if we're going to find a zero energy wave function, two things need to happen. Right? So clearly, the lead kinetic energy has to be 0, so we need to be thinking about basically k equals 0 plane waves away from x equals 0. But we also have to make sure that there's no energy cost from ht. Okay, so this piece should also give us 0. So that's the critical thing we need to figure out. How can this thing possibly give us 0 when we act on a state? Well, I guess something on the right-hand side has to be 0. Okay, so gamma, you can't really say that gamma is 0, right? Because it squares to 1. I don't really know what that would mean. So that leaves a thing in brackets. Okay, that's kind of the only thing that we can make 0 to satisfy this problem. Everyone agree with that? Okay, so this thing had better be 0 if we're going to construct a 0 energy solution. And the only way that thing is going to be 0 is if an operator language psi of x equals 0 equals psi dagger of x equals 0. So that's some boundary condition that's imposed by that coupling to the Majorana. Alternatively, in wave function language, that means that your wave functions must have equal probability of being electrons and holes, so that that piece will annihilate such a state. Okay. So if I go back to this wave function that we had here, clearly that's not going to work, right? I had at x equals 0, I had very different population of electrons and holes, and so there's no way that such a state would give me a 0 energy solution. So I need to somehow modify the structure of that solution to make sure that electrons and holes are equally present at x equals 0. It could be, but I'm not interested in negative solutions. I'm thinking about injecting electrons with 0 energy from the lead, and I want to know what happens to those. Okay. Okay, so the large T, let's view this in boundary condition language first. Large T imposes psi of x equals 0 equals psi dagger of x equals 0 boundary conditions, which again tells me that electrons and holes have to be present in equal amplitude at x equals 0. And we know once again that the eigenstates have to be plane wave-like, because away from x equals 0, the solution are just plane waves, and we just have to match up those plane waves appropriately to basically satisfy that boundary condition. Okay, but those plane waves again have to be different from what I drew here, and the only way to get consistency is that incoming electron, which we send in, must somehow be converted to a hole in the outgoing channel, so that you have kind of equal population of electrons and holes at the interface. Okay, so maybe before I write down a solution for the explicit solution for the plane waves, maybe we can just write down, kind of guess what the wave function amplitude should look like, so that I can have a legitimate solution that satisfies that boundary condition. Okay. All right, so by definition, I'm going to assume that I send in electrons, so I have no choice but to have electron part of my wave function at x equals 0 being large, and I'll take the whole population to be 0. Again, this is just the fact that I'm putting electrons in rather than holes. But this thing should crash down to 0 at the same time that the whole part gets revived. And so now you can see that at x equals 0, I have a wave function that's consistent with that boundary condition. Okay, so this is the idea of electron-hole conversion. So if I want to write down an explicit solution for an operator that creates such an eigenstate, I can write something like this: integral on x, usual plane wave part, but I'm going to put Heaviside function theta of minus x. So this is 1 at x less than 0, and 0 for positive values of x. So that's the electron part of the wave function. And so this piece is 0 for negative values of x, 1 for positive values of x, and that's the whole part of the wave function. Okay, so this corresponds exactly to this kind of wave function. Okay, so what we learned here is that an incident electron gets actually perfectly converted to an outgoing hole. So in this case, the probability of Andreev reflection goes to 1. So we have actually perfect Andreev reflection, which is mediated by coupling to that Majorana 0 mode. And since the probability for Andreev reflection is perfect, the conductance is just 2 times e squared over h. And this is the conclusion when you take energies of those incident electrons to 0. Okay, so this is actually a much more powerful result than what I claimed over here. So this 0 here is not actually that robust. If I included additional processes, you could certainly get some finite conductance even at non-zero energies. This result, on the other hand, is universal. So you can do add arbitrary perturbations beyond what I've included here in my very simplified model, add interactions in the lead, additional channels, whatever you want. This is an extremely robust result. Right? So this is a very powerful signature. It tells us that coupling to a Majorana really leads to an inevitable quantized conductance at 0 bias and also 0 temperature. Yeah.
Are there any possible scenarios of when you can get this perfect Andreev reflection? Maybe you can have other states at the end of the superconductor.
Yeah, so I'll comment on this shortly. So you could imagine a situation. Let me give you a rough scenario where something similar might happen. Imagine that you didn't actually have a topological superconductor here. Imagine that you had a trivial superconductor that had a single ordinary fermionic level, which was almost 0 energy. And so you can think about that as being kind of a weak hybridization of two Majorana modes. Okay, but to get those 2 levels to be very low in energy requires some amount of fine tuning or some special situation. But suppose that this happens, maybe you tune things around such that you accidentally pull down some ordinary level near 0 energy. If you were coupling more effectively to one of those Majorana modes than the other, then you can get something which looks awfully close to, the conductance wouldn't be perfectly quantized, but within your experimental resolution, it might be hard to distinguish. And in fact, I think one of the most important outstanding challenges for experiments right now is distinguishing between those 2e squared over h quantized conductances in the scenario where you have a true Majorana 0 mode and in a scenario where you have these accidental bound states which just for whatever reason, not due to topological reasons, happen to have low energy. Yeah.
I understand what you said at work. Would you be willing to explain how you extract the Andreev reflection probability?
Well, yeah, so technically what you should do is, okay, so let me see if I can define the scattering matrix for you. So there's a particle, an electron-like part of the wave function at x equals minus infinity. That kind of tells you the probability, or sorry, that tells you how much incident electrons you've injected. And then there's the corresponding hole part. So this is kind of what you control based on what you inject into the system. And what you want to know is the amplitude of the electron in whole parts of the wave function at x equals plus infinity, because that's what tells you what comes out. Okay, and these things are related by a 2x2 matrix, a scattering matrix. So this is the kind of thing that you would ordinarily solve for in scattering problem in quantum mechanics. So the diagonal pieces of that scattering matrix tell you about ordinary normal reflection processes. The off-diagonal pieces tell you about Andreev reflection processes. And so we can immediately back out those off-diagonal matrix elements based on what I wrote here. So I started from a configuration where p of minus infinity was 1, h of minus infinity was 0. P of plus infinity is 0, and h of infinity is 1. So that tells us that the off-diagonal element of the scattering matrix has unit amplitude, and I think the square, absolute value squared of that is the Andreev reflection probability. Okay. So more formally, that's how you can connect the dots. All right, so let me summarize what we've learned here. So our calculation, by the way, was at temperature equals 0. So if you go to find a temperature, you'll have some corrections. But let's just summarize what we know at t equals 0. So the relevant thing for experiment is the conductance as a function of bias voltage. And wherever I wrote energy, just think of energy as E times V, right, where V is the bias voltage. So when the bias voltage is 0, we found that coupling to this Majorana zero mode gives you this robust quantized zero bias peak of height 2 e squared over h. But eventually, when you probe the system at large energies, the conductance ought to go to 0, at least within the simplified model that we looked at. And so the simplest way to connect those two limits is to draw some kind of Lorentzian-like conductance. And the width of this peak, it's kind of only one energy scale in the problem. It should go like t squared over v. Okay, so that quantized zero bias peak is a very appealing Majorana signature, subject to the caveats I gave you about subtleties of distinguishing from accidentally low energy zero modes, which might happen to be present in a trivial system. And again, this is the most common signature that's been looked at so far in experiment. All right, so let me now tell you about some tunneling experiments that have been done. So there are many experiments so far done on one-dimensional wires. So the basic kind of setup that's typically looked at is you take a semiconducting wire like indium arsenide, indium antimonide, something that has strong spin-orbit coupling, because remember what we talked about last time, to get a topological superconductor, you want a system that has strong spin-orbit coupling, time reversal symmetry breaking, and proximity-induced superconductivity. So to get a tunneling geometry, I'm going to only couple, let's say, the right half of that wire to a superconductor, and we'll allow for a magnetic field, which is necessary for generating a topological phase in Majorana zero modes. So many groups have looked at such systems. Leo Kuenhoven, Matti Heiblum, Charlie Marcus, Dale Van Harling, and Sergei Frolov. So this is, there's many groups that have been pursuing these kind of systems. So maybe before I tell you what people see, we should just try to anticipate what we would expect to see based on what we know so far about how topological superconductivity forms in those kind of setups. Oh, by the way, I forgot to say, so this left half that's kind of dangling and not coupled to the superconductor, that will function as a lead. And you hope that you're going to generate topological superconductivity in the right half with a Majorana zero mode there that you can couple to with that dangling left half. Yeah?
Going back to this argument about what got you to that signature, it seems like this argument that psi minus psi dagger has to be 0, you could put anything, it doesn't, it got
Well, if I didn't have a Majorana mode, then I can't even write down such a term in the first place.
What if I should put something else instead of gamma, some other levels of something else instead of Majorana?
Well, I guess the special thing is that that gamma is otherwise a zero energy mode. So if, let's say, I put a second gamma there, then I would generically be able to couple those two gammas. Then they'll move to finite energy, and then below that energy scale, it looks like I'm just coupling. I don't have any low energy modes to couple to, and I would expect to not be able to transmit any charge into the superconductor.
It relies on you knowing that you've got Majoranas there and not having to think of different physics.
Well, okay, so the two scenarios which I can confidently distinguish is one where you have a trivial superconductor and no low energy modes, and two, a scenario where you have a topological superconductor with unpaired Majorana mode and no other low energy modes. So those two scenarios are very cleanly distinguished. Of course, you can think about murkier situations where you have additional low energy degrees of freedom in either scenario, and that's a whole other ball game. Yeah. The magnetic field? I'll remind you of this right now. Yeah. Okay, so let's think about, let's focus only on the right-hand side for the moment. And let's think about the energy gap in that superconductor as a function of magnetic field. Okay, so maybe it's useful to remind you what the band structure looks like. So I have a spin orbit coupled wire next to a superconductor. As I drew last time, the band structure, let's say in the presence of a weak magnetic field, looks something like this, right? And let's suppose that you start off with your chemical potential being somewhere here. Okay. So in this case, I have 2 Fermi points, and my system is not in the non-trivial phase. Okay, so I start off with a trivial superconductor, which is actually gapped. Right? It's gapped because you can gap out those 2 Fermi points and those 2 Fermi points via proximity-induced superconductivity. Okay, so at low magnetic fields, I start off in a trivial phase with a finite excitation gap. Okay. So in this regime, you would, if you were to perform a transport experiment, then what you would expect to see, ideally, if you measure conductance as a function of bias voltage, let's assume you have no spurious low energy modes around. The conductance should be basically 0 until, let's say, you start approaching the excitation gap for the system, and then you can, of course, start sending in charge. Okay. All right, now as we continue to ramp up the field, this splitting gets bigger and bigger, okay? And eventually, just do a little bit of blackboard manipulations here. Eventually you get to this situation where you've vacated one of those partially occupied bands. Now you have just a single partially occupied band, 1 pair of Fermi points, and now your system is topological and has an unpaired Majorana 0 mode. Okay, so that's a topologically distinct phase of matter, and just like we saw in the Kitaev chain, there should be a topological phase transition that you cross, and going from this trivial phase to the topological phase. And that phase transition should be associated with the gap closing and then reopening. Okay. Oops, sorry. Okay, so this is the field regime where I expect to have a Majorana 0 mode, and I should expect to see a quantized 0 bias conductance. And so at low fields you expect to see this behavior, but at high fields you expect to see something qualitatively different. you expect to see this ideally quantized zero bias peak emerging. Okay. Yeah.
So what way to get a wave reflection for a trivial superconductor?
You mean at low biases? That's an interesting question. So it depends on several factors. So if I have just a single channel lead, as I was assuming here, so in just one species of fermions that I'm able to inject, then it's kind of interesting. This scattering matrix that I wrote down here is very strongly constrained at zero energy. It can either be purely diagonal or purely off diagonal. Purely diagonal means basically what we recovered, no Andreev reflection whatsoever. Purely off diagonal means perfect Andreev reflection. And if you have, one can show very generally that if you have a fully gapped superconductor, no Majorana zero modes, you always have the purely diagonal form of the scattering matrix. Now, if you were to have more channels, so imagine you have spin degree of freedom, so you have a spin-full lead, then actually the scattering matrix that you find at zero energy is non-universal. And you can certainly get Andreev reflection even at zero energy, even in a trivial superconductor. Interestingly, though, if you add even a tiny amount of electron-electron interactions in the lead, the behavior once again becomes universal, and you find that the scattering matrix has a purely diagonal form, no Andreev reflection at zero energy. So it's a somewhat rich problem. Okay. Yeah.
I think the diagram is not complete, right? Because if you fully increase the field, if you exceed the upper critical field, and just destroy the proximal conductivity.
Yeah, certainly. Yeah. Yeah. So maybe I should put high fields in quote. I don't mean 50 Tesla. I mean 1 or 2 Tesla. Yeah.
So that diagram that you have to connect it to the scattering problem that you studied, is there? Should I think of it at the end of that part of the wire where there's
Here.
superconductor ends? That's where the Majorana is sitting.
Yeah, that's right. So in this topological superconductor, what ideally happens is you have a Majorana zero mode here and a zero mode here, and you're trying to probe the existence of that guy.
Here's
Yeah.
the topological superconductor, you have the peaks at the gap. Is that correct?
Yeah, yeah. Okay, so again, there are lots of experiments done along these lines. I can give you some pros and cons about these experiments. So in the last, 10 years, people have figured out ways of making exceedingly clean devices of this type. The interfaces are about as pure as they come, very high quality wires. And the quality of the transport data that has come out has improved dramatically from the first experiments that were done around 6 years ago. Beginning in 2012, starting with the experiment by Leo Kuenhoven, people first saw these field-induced zero bias peaks under precisely the right conditions that you expect them to form based on theoretical expectations. In the early days of those experiments, the zero bias peaks that they were seeing were far from quantized. They were something like 5% of the quantized values. But this was reproduced by many groups. More recently, as of earlier this year, people have now seen quantized zero bias peaks. So this is, I think, certainly very tangible and exciting progress. There's some challenges, though, with these nanowire proposals. First, actually, the zeroth order thing that I would have expected to immediately jump out at you if you do this kind of experiment is the presence of a topological phase transition. Right? That's some very dramatic rearrangement of the nature of the system. And I would have thought that this is obviously visible in conductance as you cross that phase transition. It turns out that most of the time you don't see any signatures of that phase transition whatsoever. It doesn't necessarily mean that it's not there. So what people often say is that the wave functions that are becoming gapless at the phase transition have actually very little weight on the ends of the system. Most of their weight is concentrated in the middle, and so you just have relatively low visibility for those states. Yeah.
Does the proximity induced gap also lead
I don't really. I don't think there's even a notion of a gap on the other side of the wire. Yeah, but this is a gapless system. So what you can maybe ask about is the how much pair correlation you have, and that probably I don't know the answer offhand. I would guess that it actually bleeds into the lead like a power law, but it's kind of the natural thing you would expect in a gapless system. Everything should be power law like. Yeah.
So if we actually model that system like the superconductivity or this proximity gap is like gradually change in space. So would I expect like those features will not be that robust because I would imagine it's similar to those reconstruction of the edge for those two pieces. I'm just curious.
I don't really. Okay, so you need to tell me a little bit more.
Usually we model things like we have some like mass or some other parameter change abruptly at the boundary. But if in this situation, can I think of this like gradually changing, not like a step function, but some like some slope, finite slope.
You mean the pairing that's generated? The pairing is probably fairly uniform as long as the interface is clean. But things like the electrochemical potential can change smoothly at the interface, and that's one of the those kind of smooth chemical potential changes is one of the things that can actually lead to spurious low energy modes, and that's one of the things that people worry about.
I know you would want to stick to zero temperature, but I'm curious how robust the two discrete divided edge is for like a finite temperature, like a small. Is there a small correction or just broadening or?
Well, I guess eventually, for sufficiently low at finite temperature, this becomes not quantized anymore. And let's see.
In low rate, is like a very drastically, or it's like a slowly?
It's probably some Lorentzian, I would expect. Yeah, I'm pretty sure that it's Lorentzian, at least for free fermions. Yeah.
Can you comment a bit on like dimensionality of the superconductor? And so I guess the order
Yeah.
is
Yeah, so I'm assuming that superconductor can be thought of as bulk. For the most part, I mean, actually, I'm going to depart from that later on, but certainly it's important that you don't have gapless phase fluctuations in that superconductor. Right? So we want to be realizing physics similar to the Kitaev chain. Kitaev chain, had this just rigid pairing term input. There's no phase fluctuations, and phase fluctuations can be problematic if they're there. So you don't want. This is one reason actually why you don't want to have a one-dimensional wire with intrinsic superconductivity resulting from attractive interactions, because then you only have power law correlations. But you really want long-range superconducting order for this to be robust. So you want a zero mode separated by a finite gap from everything else. Yeah, certainly. Modulo cases, again, where I'll intentionally move away from that shortly. Yeah.
If the experimentalists wanted to view the phase transition, could they wrap the lead around the superconductor a bit so it picks up more of the weight of the edge mode?
Well, I think the simplest thing you might try to do, I'm not sure if this is exactly what you had in mind, but you could try to put another lead.
It would have to cover like a large portion of it, right?
You mean this here, this width? I think it doesn't matter too much as long as you have, I think you should imagine that the wave functions that are low energy have kind of that spatial profile.
Yeah.
So as long as you put another lead which somehow is sensitive to the, is probing the position where those wave functions have appreciable weight, then I think you're okay. In fact, an experiment along these lines has recently been done by Matti Heiblum. I think it's not out yet, but.
Experimentally, can they tune B? They tune B, right?
Yeah, so that's in fact what's done in practice. You measure, you produce a bunch of traces like this for varying magnetic fields, and then you see hopefully that some zero bias peak emerges and stays put over some finite range of magnetic
So
field.
in what sense you just then say, oh, it's hard to see the transition? Isn't that the transition of the peak begins to emerge?
Well, that's I meant the bulk phase transition. Right, so this is kind of a byproduct of that phase transition, but.
Oh, I see having some other measurement that probes the bulk in the sense of the topological wire.
Exactly. Yeah. Okay. Yeah. Yeah, in fact, this is another one of my challenges actually, is that, if you just make a wire, and you don't do anything, you don't adjust the chemical potential appropriately, odds are you'll be very far away from the regime where you can get this topological phase at a reasonable value of the magnetic field where you haven't already killed superconductivity. So there's some amount of tuning that has to be done, and often, there's multiple gates here that are being adjusted. So this is a bit of an issue. You'd like somehow, ideally, the topological phase to appear more automatically without requiring any tuning. And particularly if you fast forward many years from now, when one is trying to make actual circuits for a prototype topological quantum computer, if you have to tune very carefully many wires into the topological phase, that's I think a non-trivial challenge that one would want to figure out some way to solve efficiently. And as I mentioned, I think the main challenge of all this is distinguishing from these accidental sources of low energy modes, which can lead to similar, even almost quantized signatures. And that's maybe something worth thinking about if you're interested in this problem. What kind of simple experiments can you do to compellingly distinguish those two scenarios? Okay, so there's another class of experiments that I should just briefly mention. Namely iron chains. So these are experiments that have been done by Ali Yazdani's group, Stefan Naj-Perge, my collaborator at Caltech, group at Berlin, and maybe one or two other groups as well. Here the setup is a bit different, although shares some common features with 1D wires. So here what one considers is a chain of iron atoms, which is deposited on a lead superconductor. Those iron atoms are ferromagnetic, so they spontaneously break time reversal symmetry. And that lead is a superconductor. Lead is a ridiculously heavy element, and so there's extremely strong spin-orbit coupling. So basically all of the ingredients that one has here that are necessary for getting the topological superconducting state are also present here, albeit in slightly different form. Okay. So one nice virtue of these iron chain experiments is that you can employ STM to actually spatially resolve the conductance. And these measurements have been performed, again, by several groups. And they observe non-quantized zero bias peaks, which are confined to the ends of those chains. So there's some really nice features of these experiments. There's no external magnetic field required, which is nice because ideally superconductivity doesn't like to have magnetic fields. So if you can save yourself the need to apply those, that's certainly a very welcome thing. There's no tuning that's required here. Okay, so there's no parameters that they tune whatsoever in order to enter what they hope is a topological phase. They just make these systems, do STM, and invariably they see zero bias peaks associated with the ends of those chains. So I think this is very exciting. Now the path forward, I think, towards the next step towards qubits is maybe less obvious here compared to in the nanowire setup. This is partly just, I think, a consequence of there being more work, more theory work done in 1D wire kind of proposals. But I think it's very interesting to ask, how can you go from, let's say, detecting Majorana modes in this system to doing something fancier, making a qubit, reading out, performing quantum state readout and stuff like that. All right, so that's all I wanted to say about experiments. Any more questions before I move on? Yeah.
So you said that in this case the conductance was not quantized. Was that expected, or is that like an artifact from this?
Well, let's see. Is it expected? I mean, it depends on how easy it is for you to see the conductance quantization depends on how strongly your lead couples to the Majorana. Okay, so if let's say if that coupling is if this energy scale t squared over v is small compared to temperature, then I think the peak height and the peak width are going to be temperature limited. Okay, and you won't see anything that's remotely quantized. So, to some extent, if that coupling is just weak, then you would expect to not see a zero bias peak. But exactly, what t squared over v is, I don't know. That's a parameter. In theory, I don't know exactly how to extract that from experiment. Yeah.
So is that iron trend system is also effectively like a P-way carry?
It's the same universal physics more or less as a Kitaev chain. So that assuming that there is indeed a topological superconductor realized, it's smoothly connected to our favorite Kitaev chain model, which is a 1D spinless P-wave superconductor.
So it just occurs to me that if I imagine it is not in solid state, but in AMO system, you can imagine it polarized the spin state and imagine sufficient strong interaction. And in some sense, they are also P-wave pair in 1D. So do you have any comment on this?
Yeah, I think you don't want intrinsic superconductivity. Yeah.
But layer is like finite system. So assuming if the order parameter is not like a fluctuate too much, maybe you can also see something. But I know the finite size probably also.
Yeah, it's. I think it's a pretty delicate situation, but. Okay, so now we've covered a lot of ground. So we've reviewed proposals for realizing topological superconductors in real materials. We now know at least some way of trying to detect Majorana zero modes. Yeah, go ahead.
Do you think the iron atoms are effectively spinless fermions?
No, I'm not saying that actually. So I think how exactly the topological superconducting state emerges is not so obvious. The only thing I want you to take away here is that you have all the right ingredients, spin-orbit coupling, time versus symmetry breaking, superconductivity. Whether your system looks in any way effectively spinless, that's a different question. And even what's furnishing the spinless degrees of freedom is kind of subtle. So I think it's actually, my understanding, which is imperfect probably, is that it's not that the electrons that are intrinsic to the iron atoms themselves are forming the topological superconductor. Rather, I think it's the interplay between that magnetism and the superconductor, which generates so-called Shiba states, some low-energy superconducting states, and those Shiba states are kind of hybridizing to form a Kitaev chain-like system.
There's a question about technology. Like in such structures, can the experimentalists actually measure the spin texture along the band?
I think this has been done. In here? Yeah, I don't think so. Actually, another challenge that I think I forgot to mention is that these kind of tunneling experiments really only probe the ends of the wire, and you have very limited access unless you start including additional leads to the local structure of the wires. All right, so now I want to turn to a subtler question, which is going beyond the question of is there a Majorana zero mode present, but actually how do you read out this information that's encoded through Majorana modes. Okay, so obviously if you're not able to read out the information encoded in Majorana modes, then you're never going to build a qubit quantum state readout. That's obviously a key part of the problem. So there are two strategies for performing readout in Majorana-based systems. The first involves intentionally spoiling the degeneracy. So this is more or less, what I already described with fusion. You can imagine, one strategy is to bring the Majorana modes together, intentionally split their, move those levels away from zero energy, and then try to detect their occupation using standard techniques. Essentially, the idea there is to convert the locally indistinguishable states that you have for well-separated Majorana modes into locally distinguishable states that you can detect. Alternatively, you can employ interference experiments. So that's basically a non-local measurement, which is designed to, even without bringing Majorana modes close together or explicitly spoiling their degeneracy, backing out some information by doing a non-local measurement. So I would like to give you examples of both kinds of readout methods. I'm probably running short on time, so I might have to make an executive decision. About cutting some of this. Let me think. Okay, so I think what I'm going to do is, so the first thing I was going to do is describe the so-called fractional Josephson effect. And maybe I'll just tell you in words what that means. If you make a Josephson junction, so people know what Josephson junctions are at this point, I guess, in the school, right? Okay, so if you make a Josephson junction formed by two topological superconductors, maybe I'll draw. So here's one topological superconductor, another topological superconductor, and there's your the barrier in your Josephson junction. So you can think about basically fusing these two Ising anyons across that Josephson junction. So there's some unusual behavior of this Josephson junction that we can exploit to read out the quantum state formed by that fermion built from gamma 1 and gamma 2. So maybe I can just kind of intuitively say how this goes. If I were dealing with a conventional superconductor, no Majorana physics, just ordinary gap superconductor on both sides, then single electron hopping across that junction is suppressed, right? And it's only Cooper pairs that can really tunnel. And so if you look at the current as a function of the phase difference across that junction, it goes, let's say, like sine of the phase difference, right? And it's a 2 pi periodic function of that phase difference across a junction. If you have zero modes present, then actually single electron tunneling is not fully suppressed. So if you start from, let's say, just single electron tunneling across that junction and project that single electron tunneling into the low energy subspace, you pick up some non-trivial term which is dependent on the coupling between gamma 1 and gamma 2. Okay, so the Hamiltonian that describes that coupling is something like J, some energy scale J, times sigma z, where sigma z is the thing we want to read out, I gamma 1, gamma 2, times cosine of the phase difference divided by 2. Okay, so that factor of a half is crucial here. And if you think about, let's say, cosine of delta phi as representing a tunneling term of Cooper pairs across a junction, cosine delta phi over 2 is tunneling half a Cooper pair, right? Reflecting the fact that you have ability to shuttle single electrons across that junction coherently at low energies by virtue of those low energy Majorana modes. Okay, so now the current is just the derivative of the energy with respect to the phase difference. Okay, so the current in this case will be proportional to sigma z times sine delta phi over 2. So this is a kind of weird situation, right, because I have a sine delta phi over 2. If you fix sigma z, so within a fixed sigma z sector, the current is actually 4 pi periodic. rather than 2 pi periodic. So it's qualitatively different from what you get in an ordinary Josephson junction. All right, so maybe I can just draw that. So if you were to consider, let's say, the sigma z equals +1 sector, then the current looks something like this, right? And if you think about the sigma z equals -1 sector, then the current looks like this. All right, so suppose now that you measure the current as a function of this phase difference. So you're going to get this unusual 4 pi periodic component of the current. And if you're in the sigma z equals +1 sector, then that current phase relation follows the solid line. If you're in the sigma z equals -1 sector, then the current follows the dashed line. Okay, and so by measuring I as a function of delta phi, you can then infer the thing which you're trying to read out, namely the occupation of that fermion. Okay. All right, so that's a phenomenon known as the fractional Josephson effect. It's subtle because if you there's relaxation processes that might actually prevent you from seeing the 4 pi periodicity, and that's a practical question, and this measurement has not been done, at least a DC version. Actually, I forgot to say, everything I say for the rest of my lecture is experimentally untested, and so you should view everything with a grain of salt and try to come up with better ideas for everything that I tell you. Yeah?
So is there some background signature of like 2 pi periodicity such that?
Thank you. Yeah, so indeed that's true. So this is not the full current, so there's an additional, with a different numerical factor, sine delta phi piece. But the important thing is that even with that extra sine delta phi piece, the current is 4 pi periodic function. Yeah. So. Okay. So in my notes, I'll say a lot more about that fractional Josephson effect. So if you're interested, you can consult notes which will eventually be posted online. Yeah, you could have higher harmonics as well, but
there's a possibility of following sigma z equals +1 and then switching to sigma z -1.
Exactly. So that's yeah. So it's kind of strange to even how can you possibly have a 4 pi periodic function? Actually the microscopic Hamiltonian is 2 pi periodic, so what's going on, right? It's some puzzle there. So the idea is that if you start in the ground state, let's say at delta phi equals 0, and then advance the phase by 2 pi, you go to an excited state. Okay, so there is a ground state with the same energy that you had at delta phi equals 0, but there's some conservation of fermion parity basically prevented you from returning to the ground state. Okay, so you had to, if you want to go back to the ground state, you have to wind the phase by another factor of 2 pi. So, in principle, in theory land, if fermion parity was really completely conserved, then it would take you infinite time to, if you ended up in that excited state, you could never relax back to the ground state. But, there's something called quasi-particle poisoning. You can find fermions basically from the environment or God knows where, which will allow you to relax back into the ground state. And if that happens, then your 4 pi periodic current becomes 2 pi periodic, and then you lose the ability to perform readout. So if you want to use the fractional Josephson effect to perform readout, you have to have fermion parity conserved over the time scale at which you do the measurement. Okay.
So is that like effectively you treat it as some closed system? In some sense, like the particle number is the same.
Well, the fermion, just the fermion number has to be the same. Yeah. Yes, that's true. Yeah. So there's also okay. So technically, if you remember that are additional Majorana modes out there that have some non-zero overlap with gamma 1 and gamma 2, then if you were to perform this cycle purely adiabatically, then you would indeed be able to go from the ground state and then find the ground state. Essentially, those outer guys give you a source of an extra fermion that allows you to relax back into the ground state. But that splitting is in a nice device will be exponentially small, and so you have to basically perform the cycle exponentially slowly in order to follow that ground state. So basically just Landau's inner physics, right? You want to make sure that you don't know about that avoided crossing that's generated by those couplings. Okay, so let me go through a different idea for readout. This involves what I'll call parity to charge conversion. All right, so now I'm going to intentionally make my entire topological superconducting system mesoscopic. I want to make it relatively small. So these are the Majorana modes that I want to read out. So this actually probably is also familiar to you guys from people that discussed transmon physics. If you have isolated superconductor, then there's a charging energy term, and if the system is sufficiently small, then the capacitance can be sufficiently small that it costs you appreciable energy to even add one electron to the system. Does this sound familiar? Okay, well, that's okay. This is actually freshman electrostatic physics, right? So if I have just an isolated box, which has some amount of charge, the energy cost for charging up that box is q squared over 2c, where c is a capacitance, q is the total amount of charge. Right? So the only thing I'm invoking, the important aspect of this thing being mesoscopic is that capacitance is tiny, so that changing the charge from q to q plus 1 incurs a measurable energy cost. Okay. All right, so that's one ingredient I want to invoke here. I'm also going to introduce a second trivial superconductor, which I'll assume is grounded. And I'm going to connect up this mesoscopic topological superconductor and that trivial superconductor with a tunable barrier. And by tunable, I'm imagining that you can vary the strength of the barrier from being basically infinite. So if the barrier is infinite, then that's like sort of cutting the system in two, right? And then you basically just have an isolated mesoscopic topological superconductor. I'm going to assume that you can go from that infinite barrier to basically zero barrier, in which case there's very efficient communication, in particular shuttling of Cooper pairs across that system. Okay. All right, so let me write down a toy Hamiltonian that captures the physics that I'm interested in. There's going to be two pieces. There's going to be a Josephson coupling minus j cosine delta phi hat. So delta phi hat here is an operator. So that cosine term just shuttles Cooper pairs, charged 2e objects from here to here, right across that barrier. And I'm assuming that I have the ability to tune j, right, by controlling the height of that barrier. That's a Josephson coupling, and I'm also going to include a charging energy term, which I'll write as u times n hat minus n0 squared. So you haven't seen Hamiltonians like that in the school so far? Okay, I thought you have. Okay, sounds good. All right, so this n0, that's I'm assuming that that's some gauge tunable offset, which just tells you how much charge would ideally like to sit on that mesoscopic part of the system. Here, n hat is an integer. That's going to count the total number of electrons on that topological region. So I want to emphasize that that's the total number of electrons. It's not the total number of Cooper pairs. Okay, so that basically because we have these gamma 1 and gamma 2 operators, we should be able to accommodate either even or odd number of electrons on that region. Okay, so as I mentioned, cosine delta phi hops Cooper pairs back and forth. Abbreviate Cooper pairs CP. And because of my definition of n as being an integer, which counts the number of electrons rather than the number of Cooper pairs, this term changes n hat by 2, okay, not by 1. All right, so that's the model I'd like to consider. So to start out, I want to think about what the spectrum of that Hamiltonian looks like in the case where that tunable barrier is infinite, in other words, where J is 0 and I only have that charging energy term. So while I erase, maybe just think about what the energy levels look like as I, let's say, vary that offset n0. Okay, so let's think about energy as a function of n0. At j equals 0, the Hamiltonian is kind of trivial because the eigenstates are just labeled by n hat, which in turn tells us how much charge sits on that part of the system. So basically, the energy levels just look like a bunch of parabolas corresponding to different values of charge. Okay. So let's say here's the parabola corresponding to n hat equals 0. Here's the n equals 2 parabola, 4, and so on. I'm going to indicate the even guys by solid lines and the odd ones by dashed lines. So there's 1, 3, and so on. Okay, so notice that unless you fine-tune n0 to one of these crossings, in general there's just a unique ground state, which corresponds to just states that have a fixed amount of charge on that system. So there's no topological degeneracies in this regime. Okay, so we've spoiled those basically by incorporating this charging energy term. So again, we just have non-degenerate charge states. Okay, so that's one limit. Now imagine that we take that infinite barrier and begin to relax it a little bit, so we can turn on a little bit of J and allow some Cooper pairs to tunnel back and forth. All right, so it's no longer so easy to solve that Hamiltonian, but we can kind of deduce, roughly speaking, what ought to happen based on this J equals 0 plot. So that cosine mixes states with the same fermion parity, right? So for example, states with charge equals 0 and charge equals 2, those will be mixed in response to that cosine delta phi piece. And so we're going to generate avoided crossings wherever we have two levels that meet with the same parity. Okay? But notice that I won't actually get an avoided crossing between the 0 and 1 states because those differ by 1 electron, and that cosine term doesn't mix those sectors. Okay, so the spectrum will look something like this. Okay, so this probably looks familiar, right, from previous lecture, I'm guessing. Okay. All right, so now let's imagine we reduce that barrier even further. In other words, crank up J to the point where it's actually much larger than U. Okay. In this case, these bands basically just continue to flatten, and in this regime where J is much larger than U, the bandwidth there becomes exponentially small. So I'll draw this in a somewhat exaggerated fashion. And so that the difference between, let's say, the minimum and the maximum of that lowest state goes like e to the minus some number times square root of J over U. Okay, so in this regime, we have within exponential accuracy degeneracy between even and odd parity states, and that's the degeneracy that reflects the presence of Majorana zero modes. Okay. And those even and odd parity states correspond to values of sigma z, which as usual is I gamma 1, gamma 2, just being plus or minus 1. Right. Okay, so let's now imagine that you park yourself at some particular value of n0, and suppose that you initialize your system is in the even parity state. Right. So if we now start raising the barrier and decreasing U, so let's go in this direction. We can follow what happens to that state. So here, these even non-parity states are almost degenerate. That splitting is increasing, and eventually these states are very different in energy. Okay. So the nice thing about converting these almost degenerate parity states to non-degenerate charge states is that it's an amazing fact from mesoscopic physics that you can straightforwardly measure how much charge is sitting on that isolated island, okay, using charge sensing technology. So I can then introduce the charge sensor to my system and measure that there are indeed 2 electrons on that island, which in turn tells me that I must have been in, let's say, the sigma z equals +1 sector. Conversely, if I started in the odd parity sector, then I would end up in the ground state at that particular value of n0, and I would wind up determining that there is 1 electron rather than 2 on that island. Right. So I can, by going from here to here, I can perform readout. So again, measuring n hat allows me to infer the state of my Majorana modes. So that, I think, is conceptually very nice. It's challenging. I think in particular the main challenge with this approach is having enough tunability of that barrier so that you can actually go from the regimes where J is very large compared to U all the way to the limit where J is 0 or approximately 0. That is not yet established technology as far as I'm aware, at least in these in the devices that we care about. Yeah, you can indeed. Maybe I should comment on that. So suppose you couldn't actually go all the way to J equals 0. That's actually okay. You could incorporate transmon technology to basically the difference in excitation frequency in the even and odd parity states is different, and by measuring that shift, you can also infer the state of your Majorana modes. Okay, yeah.
If you have 2 trivial superconducting dots and just a couple between them, such that the charging energy is large, so you're in mesoscopic limit, shouldn't you also have 2 2-pi periodic sets of dispersions, one having to do with odd number of quasi-particle on that superconducting dot, and not having a quasi-particle?
Yeah, so that's right. So let's take away the Majorana modes and just assume I have a mesoscopic trivial superconductor. What changes here actually is that the odd parabolas actually get shifted up, and they get shifted up by an amount delta, where delta is the excitation gap, which basically tells you that you can't, it's unfavorable to have an unpaired electron on that island.
And here, if you tune n0 correctly, it's degenerate.
Yeah, so, yeah, that's right. Yeah. But I don't think you want to necessarily do that. In fact, you probably don't want to tune to degeneracies.
So the difference is that without the charging energy, the odd and even are degenerate, while in the ordinary one, odd, even, and are split by delta.
Exactly. Yeah. So maybe I can also say what happens in this limit when you have an ordinary superconductor. Basically, the solid and dashed lines are just, they're not even close to degenerate. They're split by an amount delta. Yeah, I think that's actually another nice way of looking at the special physics of these Majorana devices. All right, so let me quickly say something about interference. I'm once again going to take a mesoscopic topological superconductor, and I'm going to assume that it's in the the regime where you have a large U. Okay, so that means that I have a unique ground state, and I'm going to assume that my system starts in that unique ground state. And there's an energy cost of order U to populating an extra fermion on that system. Okay, so basically I'm just parking myself at some gate voltage like this, where I have, let's say in the ground state I have 1 electron, in the excited state I have 2 electrons, and to have that second electron in there costs me an energy U. Okay, so let me dress up this setup a little bit. I want to introduce a pair of leads, one of which coupling couples to the left Majorana, and the other which couples to the right Majorana. All right, so both of these are leads. Now suppose that you had an electron from the left lead, which I'm going to call CL. Suppose that electron jumped onto the island via coupling to gamma 1. Right. So now you have an extra electron on that island, so you've been taken away from the ground state. Right, so that you've now accessed that excited state. Now the key thing here is that there's a single fermionic level which is shared non-locally between gamma 1 and gamma 2. Right. So if we think in perturbation theory, we eventually want to get back to the ground state, but we can get back to the ground state in an interesting way. Okay, so we don't necessarily have to pull that electron back from where it came from. That electron can move from gamma 2 onto the right lead, where it becomes an electron that I'll call CR. Okay, so in that process, you return to the ground state. So this mesoscopic topological superconductor mediates some non-local hopping from the left lead to the right lead. So if you do second order perturbation theory, you can extract an effective Hamiltonian for this process, which goes like t squared over u, where t is just the hopping amplitude onto one of the Majoranas. By the way, I use t in a zillion different ways in this lectures. I hope that's not confusing. Okay, so there's an overall energy scale of order t squared over u. Then there's a sigma z, which is I gamma 1, gamma 2. That's the thing we are interested in detecting, times c left dagger, c right. Okay, so notice that this is not an ordinary tunneling term because it involves this sigma z. All right. And so I'm not deriving this for you. It's actually a little bit, one could do this, but in the allotted time, there's no chance. But I can at least maybe give you some technical reason why you won't have an ordinary tunneling term that does not involve sigma z. So actually, the underlying Hamiltonian here is invariant under, let's say, changing both CL and gamma 1 by a minus sign. And similarly, you can change independently gamma 2 and C right by a minus sign, and the system looks the same. So this Hamiltonian that I wrote down preserves that symmetry because I have this factor of sigma z in there. But if I didn't have that sigma z, then I would be violating a basic symmetry of my microscopic Hamiltonian. Right? So this is really unavoidable. All right, so what this presence of sigma z tells us is that the electrons, when they make their way from here to here, they pick up a phase which is dependent on the occupation number that I want to read out, on the sigma z variable. Okay. So there's a phase that I want to read out. So how do you detect phases in quantum mechanics? Maybe think about it, and I'll just write something on the board. Okay, how do you measure phases in quantum mechanics? Interference, exactly. Interference is the way to do it. So I don't have an interferometer in what I've drawn you so far, but I can easily make it into an interferometer by adding a reference arm.
Is the matrix element, like the tunneling matrix element, the lead onto that Majorana chain? Is that small, not just especially small in the sort of in the left, just in the barrier on the left side, but is it also suppressed by how far the gamma-2 is from CO? It feels like it's, you try to put a fermion on the left end, but that fermion really lives across, along the whole wire.
Yeah, so
Suppression with the length of the topological superconductor.
So it's pretty counterintuitive, but I think the only influence on length is actually through basically the capacitance. Right? The capacitance will change, U will change.
Tunneling is not.
The tunneling, this just is a property of, how local property of that interface.
Even though that gamma-2 is far away.
Yeah, so there's also, maybe I should say that the interference that I'm going to invoke in a second requires phase coherence, and there can be dephasing that happens in intermediate times, when your electron is going from left to right. And so if your electron spends too much time in this region, then you will lose the signal that you're trying to back out. So there's also that physics, but I'm not sure that that's a very, that time scale probably is not very sensitive to the length of the device. That the propagation, I think, basically happens at speed of light. So that, it's very counterintuitive actually that this has such weak length dependence. And in fact, that the very weak length dependence here is one reason why people actually want to use topological superconductors as reference arms themselves to make an interferometer, because they can potentially allow you to perform phase coherent transport over very long distances. I'm not going to invoke that in this case, but it's all right. So we need to add a reference arm in order to make an interferometer. So let me just modify my setup in a straightforward way. Right, so that is an interferometer. So electrons from this lead have two paths that they can take to go to the right lead, right, either below or up top. It might be that, let's say, for sigma z equals +1, maybe the transport through the upper loop interferes constructively with the path through the lower loop. If you change sigma z to -1, you would spoil that perfect constructive interference, and you'd get a different probability for tunneling all the way across. So what you can measure here is conductance. And that conductance G will generically have the form G0, some G0 plus sigma z times delta G. All right, so if you were to measure the conductance, then that in turn allows you to infer the value of sigma z. Okay.
Can you say fermion propagates exactly the way that superconductor with the speed of light, you said?
Well, okay, so you basically want to ask, how fast does it take for a blip of charge to delocalize? and there's some kind of plasma frequency that sets that and that speed. Okay, so this is actually a very powerful idea. It's interference-based readout. You can actually perform this kind of interference-based measurements to perform braiding operations. So there's so-called measurement-only topological quantum computing, which affects braids without actually moving anything, but rather just performing some sequence of projective measurements. You can also adapt this interference idea to perform measurements of multiple Majoranas, not just 2, but 4, 6, 8, and so on. And that's useful actually for higher order applications. If you want to, let's say, get a 2-qubit entanglement gate, you're going to need the ability to measure multiple Majoranas without measuring individual pairs, and this gives you a way of doing that. But again, it's not established technology. We need to see whether this actually works out. Okay, so I can see that I'm basically out of time, but maybe I can say, just take a few minutes. Is that okay? To just say some wrap-up thoughts. The last stuff I wanted to say concerns how do you actually characterize a qubit. So once you detect a Majorana mode, demonstrate the ability to perform readout successfully, then next step is to try to verify or maybe otherwise the unusual properties that are expected to exist in these Majorana-based qubits. So first of all, what does a prototype topological qubit even look like? I think we've discussed this maybe indirectly several times, but a system with just a pair of Majorana modes is not a good qubit. That has 2 ground states in principle, but they're in opposite fermion parity sectors, and you can't actually coherently mix those opposite fermion parity sectors. So a minimal topological qubit actually has not 2, but 4 Majorana 0 modes. And so the logical qubit states that we can use here correspond to, I can, let's say, define a logical 0 to be I gamma 1, gamma 2 equals +1 state, while simultaneously I gamma 3, gamma 4 is equal to +1. So that, let's say that state has even fermion parity. I can define another even fermion parity state, which will be my logical 1, by just taking both of those values to be -1. We can actually superpose those states because they have the same fermion parity. All right, so I think an interesting question to ask yourself is, suppose somebody hands you this device and they say, okay, we know for sure Majorana modes are there. Here's a proven readout strategy. What are you actually going to measure? Right? So I think this is not a completely settled question. I think at a minimum, there's 2 kind of things that you would like to do, at least in first generation experiments. You'd like to verify that qubit is at least behaving like a fault-tolerant quantum memory. In other words, you can store quantum information in that system for long times, reflecting the local indistinguishability of the ground states of your 0 and 1 qubit states. But how do you do that? Actually, it's an easy thing to put on your wish list, but what experiment are you going to do to actually put meat on that statement? Okay. So you might say, well, just measure, let's say, the dephasing time of the qubit. Maybe you get, I don't know, suppose you get a microsecond. Is that good or is that bad? I don't know. I think you want a more universal way of characterizing the qubit. And I think one way of doing this is to exploit actually the imperfections of the qubit. Right. So ideally, those 0 and 1 states are exactly degenerate, but that's never going to be the case in reality. So those 0 and 1 will be split by some amount omega, which goes like e to the minus L over c, as we've said previously. And that c depends on various parameters, chemical potential, magnetic field, and so on. Okay. Now for a good topological qubit, this is going to be a minuscule number, but for a bad topological qubit, it'll be a fairly sizable fraction of, let's say, the bulk gap. Right?
Isn't there also, there's also mesoscopic contribution to the splitting, which is power law?
Well, you mean from the charging energy?
Yeah.
Well, that would be another exponential if you operate in the regime where J is much larger than U. So I'm assuming that that's settled. So yeah, this could either be arise from residual charging energy or from just explicit overlap. So I'm just going to focus on this, although the spirit of what I say would hold even in that, if that's a dominant source. All right, so let's think about what omega looks like. By the way, that omega is the qubit's natural oscillating frequency. Right? So obviously, this depends on a multi-dimensional space of couplings, which I'm just going to compress into one axis, which I schematically call G. So this is, who knows what this looks like, but suppose you have some characteristic behavior like this, where if you're out here, so this is omega. This is the limit of a bad topological qubit, so you have sizable splitting, and down here you have a good topological qubit where the splitting is starting to get minuscule. So alternatively, the states up here are not very locally indistinguishable from each other, but here they're starting to get very locally indistinguishable. Okay, so suppose now that you have a qubit and you're sitting somewhere there. Right? So invariably there's going to be noise in those couplings, right? So there's going to be some random variation of those couplings, which I'll schematically denote by delta G. Chemical potential fluctuates, random chemical potential fluctuations, and so on. And that's going to cause that frequency, natural oscillating frequency of your qubit, to wander, in this case over a fairly wide window. Right? And so those random variations of that splitting causes dephasing and will lead to some finite T2 time. Now as you make your way towards a good topological qubit, the same amplitude of those random variations cause relatively small wandering of that frequency. Right? And this is again reflecting indistinguishability for qubits, and correspondingly your T2 time should be much larger. So this is omega. If you plot T2, it should have the inverse behavior. T2 should actually become arbitrarily good, arbitrarily long, as you make your topological qubit arbitrarily good. So there's actually scaling behavior that one can try to exploit for a topological qubit. In particular, the oscillation frequency and the inverse of the T2 time should be correlated with one another and should both go to 0 in the limit where your qubit becomes perfect. Right? So obviously you'll never reach that 0, but if you can see this inverse relationship, actually both of those things should become exponentially approaching 0 as you make your way towards a good topological qubit. So verifying this behavior, backing out omega and T2 and understanding how the qubit evolves as you make it better and better, that I think would provide a very nice way of validating that there is indeed some topological protection that your system is enjoying. All right. We definitely need other ways of trying to verify this behavior, but that's just one idea. The other thing I was going to say pertains to braiding. Actually, I don't have that much to say. It's obvious that next order thing you would like to try is to, let's say, braid a couple of these Majorana modes. You'd be demonstrating non-abelian statistics, and at the same time, hopefully, demonstrate the ability to perform topologically protected gates. Both of those would be, monumental achievements, of course, as would, just showing that you have a topological quantum memory. I'll just maybe quickly say that a braid, let's say if you initialize yourself into the 0 state, braid gamma 2 and gamma 3, that corresponds to ideally a perfect pi/2 rotation on the block sphere. So maybe the last thing I'll say, I apologize for going too much over time, but how do you actually verify that behavior? That's also kind of an interesting question. So one thing you could try to do is initialize into the 0 state, perform a braid, get this 90-degree rotation, and then read out, and you should get equally likely. You should be equally likely to find your qubit in 0 versus 1. So you should be very, very excited if you get a random answer right at the end of the day. But okay, random answers, well, sometimes nice, can also arise for trivial reasons. So you want a more satisfying protocol. So I think there's a very completely unambiguous way of associating that pi/2 rotation with braiding as opposed to some random nonsense that happened during the protocol. Suppose you do not one braid but two braids. Okay, so this is corresponding to 2 pi over 2 rotations, which corresponds to a pi rotation. In this case, you would just perform a bit flip. If you started in 0, you'd get 1. And then if you measure, you'd get a deterministic answer. And the odds of 1 braid giving you a random answer from nonsense and 2 braids giving you deterministic answer, I think that's basically 0. Okay, so I should quit here. Again, apologize for going over time. I think there's lots of interesting directions left in this problem. I hope some of you will be interested in pursuing this endeavor. And thank you for having me at your school. It was a lot of fun. Okay, maybe I shouldn't take questions in the interest of time. Yeah, go ahead.
So just one quick question. So how are you going to generate a 2-qubit space out of this one? Because the moment that you braid with either one of them with the 5th one, and then you leave that subspace, right?
You have to perform restrict yourself to operations that keep you within the qubit subspace.
2-qubit gates with that sort of qubit is already not.
Yeah, 2-qubit gates actually require multi-Majorana measurements. So it's beyond what. Yeah, so these are just really good for single qubit gates. Yeah.
Do we expect to do measurements using, for example, this parity charge conversion at a rate faster than the e-to-time scale dimension?
Well, I hope so.
Because it looks like a lot of tuning and, well, the e-to-time scale, you said the small parameters in such a very small.
Well, I mean, I have nothing to say about that apart from, that's certainly, you need to be able to convert whatever, perform readout on a time scale which is fast compared to the rate at which your information is just going to be randomized. That's actually a serious issue because, for example, if I want to do parity to charge conversion, I have to fairly dramatically readjust my system. And I might not be able to do that over a sufficiently, short time scale. Actually, that I think I don't think that matters too much. So I think what you're worrying about is, once I make omega large intentionally, then my qubit is very susceptible to dephasing. And that's of course true, but we don't care at that level because I'm performing readout, and I might spoil superpositions, but that's the name of the game because I'm trying to read out. But what you don't want to happen is, let's say, how should I say this? Well, suppose that I want to read out 0, and somewhere along the way, as I'm trying to read out 0, I have an error which mixes in appreciably 1. That's gonna be problematic. That's the kind of thing you don't want to happen. But for instance, it's perfectly fine if I suppose I have a superposition of 0 and 1 with a well-defined phase relationship. I can spoil that phase relationship during readout if I'm reading out in that basis because I'm just reading out the absolute value anyway. So that's okay. Yeah.
So if any one of these state readouts protocols work, then does this eliminate all other candidates for like the conductors?
I would say.
All based on degeneracy, right?
Yeah. So suppose you saw. Wait, actually, sorry. Are you referring to the latter stuff?
The readout, like
readout.
Effect or the interference, they all are based on degeneracy, right?
I think those don't necessarily. I think you can have almost all of that behavior even with trivial states. So readout, I think, is not necessarily going to. You hope that if, let's say, you measure this DC fractional adjustment effect, that it would be very unnatural to find that behavior in an ordinary system, but it's not out of the question. In fact, I think there's even a recent paper that says, maybe even with the title, fractional adjustment effect in trivial systems, something of that nature. So,
again, related to the degeneracy of the.
At some point I mentioned that if you have, let's say, 2 Majorana modes which are close but happen to not overlap very much for accidental reasons, you can imagine a pair of those being sitting opposite a Josephson junction, and you would find very similar behavior to what I discussed here if only half of those Majorana modes are actually coupling to each other. So this is the kind of thing people worry about. But this behavior, I think I can't imagine a scenario because this is really exploiting a much more sensitive characteristic of separated Majorana modes, which is their insensitivity to noise. Right? So if I have two Majorana modes which happen to be close but are accidentally not overlapping very much, that's a statement that requires some fine tuning, and noise is certainly going to produce some much larger splitting than what you would get for well separated Majorana modes.
Okay, maybe on this note, let's break for coffee just for the
Sure. Yeah.
after Jason's